Next up, I'm delighted to welcome to the stage John Overton, CEO of Kove, and Bill Wright, AI Technology Evangelist at Red Hat, for their discussion on software-defined memory, tackling AI's challenges now with memory flexibility. Welcome, John and Bill.
Good morning, everybody. Thank you for being here today. We're really excited to have you. And it's really a delight for me to introduce my friend, John Overton, today. But before we get started, I'm going to ask a few questions. How many of you are running applications in your data centers that cause memory contention, memory issues, or memory bottlenecks, like AI training runs or in-memory databases? How many? Could I see a show of hands? Oh, I got a few hands. What a surprise. And how many of you would like to see those bottlenecks go away? Oh, that's a lot of hands. Look at that. And I would also add, how many of you would like to, beyond that, use existing hardware, existing memory, to achieve the flexibility you require to get rid of those bottlenecks? Any hands on that? Yep, got a few. And as expected. And then the other thing I'd like to ask is, how would you, in addition to this capability, like to see a 15% up to 50% power reduction in your data center as a result of using this technology? Yeah, I see a lot of like, yeah, show me, prove it. And that is exactly what we did at Red Hat with Kove. When we met John and his team, we were delighted by them because they're very, very much the traditional startup, but they've been around for years, for decades now, working in supercomputer environments, and they're now just becoming, I guess you could say, marketing ready from that perspective. But in terms of technology, it is absolutely the most profound thing I've seen in about 15 to 20 years of being in the cloud computing business. I've only got a few minutes, but I'll give you a little bit of background. I worked in the very earliest days in terms of characterizing business intelligence workloads and telecommunications workloads, which led to NFV in the early days of cloud computing. And back then, you kind of didn't know what to expect. There were a lot of behavioral characteristics you'd run into, and that would really kind of take your hardware like in completely new directions. If some of you were around back then using certain business intelligence applications, which are the predecessors to what we're seeing today with AI, sometimes they would actually have instruction sets that would spin up all the resources of the server farm just to add a couple more percentage points of performance. So not a very good ESG story at the time. Of course, they've changed since, but what was interesting is there were behaviors you could never anticipate. And the one brick wall we always ran into was memory. You could virtualize so many different components in so many different ways, but memory, you just assumed there was nothing we could do about it. It was just going to be static. That was just going to be where that was. Everything else was flexible. Well, that has changed today thanks to Kove. And when we took Kove into the lab and we ran multiple performance tests, we really tried to bring it down to its knees. There was no way to do it. And I'm speaking as Red Hat, as a partner of Kove. I mean, on the infrastructure side, we're very careful about how we present new technologies to our customers. Kove is everything as advertised. It's really fantastic. So with that, I'd like to turn this over to my friend John, and please take it away.
All right. Thank you, Bill. So what is Kove? We are actual virtualized memory. This isn't storage class memory. It's not NVMe over a network. You can put a server over there, and you can put memory over there, and it performs the same plus or minus 1 or 2% as the memory in the server over there. You can actually do that for almost 500 feet. We can hide the latency. We don't kind of hide the latency. You don't need anything special. You just need to install some software on any hardware that you've got. Now, what's the punchline of where this leads us to? Well, it leads that you start thinking to build AI models or anything else you want to build, irrespective of your compute infrastructure, in a way that you didn't before. The implications are a whole bunch, which we're going to go through as we go forward. So let's imagine, this is a picture of kind of the way you would think about it. The middle, the middle K is a memory pool. It is any kind of piece of hardware that you have that has memory in it that is x86. It's actually the AMD 64 specification, so it's pretty much anything. And then you have servers. And those, you can have any amount of servers. There's no limit. It scales linearly. So if you want a terabyte a second of bandwidth, or you want 10 terabytes a second, you can get that. The obvious question, of course, now I've got this set of cables in the middle. So what's the latency, right? Everybody knows you can't solve that problem. It's physics. It's the speed of light, distance of cable. You can validate this. Anybody can validate this. Red Hat validated this. I can put the server over there. I can put the memory over there, and it's the same performance. The latency is 10 or 15 nanoseconds. That's the same latency of draining from memory into the CPU at scale. Let it hit you. Now let's imagine you want smart cities. Okay, let's think about latency. I'm going to bounce up to the satellites, and I'm going to bounce down. I'm driving my car. Blink your eye the next time that you're driving your car. Think about where the car goes. That's the cost of going up and down. Okay? Now let's say I want to do training on smart cities, and I have thousands or tens of thousands of servers. Well, the big problem, of course, is it's too expensive if I'm going to buy clusters, small clusters, and I'm going to put thousands or tens of thousands of those, let's say, across a country. It's too expensive to fill them with lots of memory. What if you could just move the memory around? That's what that is. And it just works. Okay, now let's imagine the day in the life of training. This is designed to be very kind of rudimentary, just to let ourselves wrap around. You have a workflow, and you're going to spin through that workflow. Now let's just imagine that I'm a big company. I've got 50, 100 data scientists. I've got my big clusters of systems, and I want somebody to run something on that. So I wait for my moment to queue this up, and that's my moment. I segment my data to fit on all of the servers that I can fit, and if one of those servers goes above the size of the local memory, then it hits NVMe, okay? In the best case, a swap. That's 125 times slower than DRAM. Now, that sounds like a lot, but let's give you some numbers. So if you were to train that job in 4 hours and you hit NVMe, it takes 19 days. I'm going to train that 1,000 times. Anybody still want to be alive by the time you do that? You don't do it. So you turn off the swap, so you crash your job because you don't want to anger all of your colleagues waiting 19 days to get something done, right? This is a solved problem. Like, it doesn't have to happen if you don't want it to happen, period. So what that means then, let it hit the back of your brain. What if I let the hardware shape shift into the needs of the model, right? Rather than the model be crammed into my hardware. So you can't even think about that being the case, because if you use any kind of storage class, whatever you're going to call it, whatever the other, you can't. And now imagine you're going to train that for 1,000 times before it goes into production. You can't, so you don't. What if that just never was the case, ever again? Because you could use any hardware that you have in your data center or on the edge, and you moved the memory to the compute in real time. So anybody want to guess how long it takes us to construct that? It takes 200 milliseconds. So literally in the time you blink your eye, you can build a 100 terabyte server. Literally, in the blink of your eye, you can move memory to 50 different servers, the exact amount needed for 2 minutes, 7 minutes, whatever the provisioning that you want to do. This is now. There is no need for CXL. There is no need for specialized hardware. You don't have to buy anything new. You just have to install some software. And you can validate this on your own code base with no code changes, on your own hardware with no effort, hardly. Okay, let's see, let's give some numbers because, first of all, there's the big question of what's the latency? And look, every person here is probably very, very, very technical. And when I say there's no latency, you have every right. It's very reasonable for you to say, I don't really believe this because I know I've been trained for 30 years that this is not possible. All I can say is validate. They did. Okay? Supermicro did. We have people all over the world who are validating this. You can validate it. Just try it. Now, we have a customer, and they were having trouble getting GPUs, because it's really easy to buy $40,000 GPUs these days, right? Everybody just goes to the store, you say, I'd like one, somebody says, here you go, and none of the 5 or so big techs have bought all of them. So for the rest of the mere mortals and the enterprise, you have to still go forward. So what do? Well, this particular customer had VMware. They've been using VMware for decades. It's the go-to platform. And they wanted to test, us against VMware. It's really OpenShift and us and Red Hat. So they first did it, and the results were so startling that they didn't believe the results. And this is remember, speed of light, distance of cable, can't solve that. Can't put the memory over there, right? So they didn't believe it. So they deinstalled all of this so that they could have the same hunk of metal with the same CPUs, the same everything. This is after they had already done the testing. And then they installed OpenShift and Red Hat and Kove. The results, the same exact everything, as in the physically same everything. The partnership that we have was 60 multiples faster than VMware, okay? So you can buy 60 computers, or you can buy one with us. Or you can wait 5 years until you get GPUs. That's another good one, okay? So the next thing that we did is that, he was mentioning this before, we got Supermicro and Red Hat, and Kove wasn't involved in this. We oftentimes have folks that kind of don't believe the results initially, so they tested a lot, billions and billions and billions of tests. And they wanted to see what the impact on power would be. Think about if you're going to be doing edge computing. We're here at Edge, so I'm going to have tens of thousands of servers across the country. I'm going to be doing as much as I can. What's the power signature that you have if you're in an inverse relationship? I buy big memory, and I have big power and big money. I buy small memory or small compute, and I reduce the money, but I'm less capable. So I then get my smartest people to figure out what's the right kind of stamp for this kind of load. I put that here, I get another stamp, another load over here, and I keep doing that. Or I'm standardizing because I got to support it. Okay. If you use our software with Red Hat, they have measured, and these are using voltmeters, a 54% reduction. It's actually 12 to 54% power reduction. There's literally no code changes. How is that possible? Well, if you can move the memory to the compute, you can buy less memory because the memory is flexible to move to the compute. Only when needed, because it's provisioned. Server over there, the memory over there. That works just as well when they're right next to each other in an edge scenario, just as well. So I buy less capable servers from a memory perspective that are going to do the computation, a lot less capable. 64 gig server can become a 1 terabyte server on the edge in the time it takes you to blink your eye or to consult a satellite. And now you've created a custom server configuration for a given model, for a given moment in time. And when that's done, you can relinquish the lease, it goes back to the system, and the next process can make that same request. It's really like virtual memory inside of a server, except it's virtualized memory outside of the server. Now, this concept is not at all old. Every technology has gone through this. You build some big specialized something or other, and then it gets commodified. And once it gets commodified, it goes into more common hardware, and then after that, it becomes virtualized. Storage, networking, computation, et cetera. People haven't figured out how to do it with memory. We have 65 patents on this issued worldwide. Everyone in this room, you may or may not know it, but you use inventions that we have made. And we'll talk a little bit about that toward the end. The next measurement that was done was everybody knows what you have to do is get smarter with NVMe or some kind of flash technology, a new fancy memory technology, because that's going to be the future, because we want to make the server stamp ever increasingly good, right? That's the future. It's the past. What if you didn't have to do that? Just like it used to be that you would have to put big disks in servers in big mainframes, and you don't have to now. Well, what if you didn't have to do that with memory? So measurement, you can put the memory over there, you can put the compute over there. It's plus or minus 10 to 15 nanoseconds different than the local memory, so it's basically the same speed as local memory. And if you take the fastest NVMe that you can purchase and you stick it on the motherboard, it's 125 times slower. Again, that's not us saying that, that's measured externally. And with that, I am going to hand this over to my colleague.
Thanks, John. I know this is all very hard to believe at a certain level. Some of you may think it's possible, but I suggest you take Kove technology, put it into your labs, and test it for yourselves. It really does work as advertised, and particularly in the case of OpenShift AI, we find it to be a very compelling technology from a number of perspectives. And when you think about OpenShift AI, I can go through all the details as needed, but quite honestly, what it is really from the inception of an application all the way up into a production deployment, OpenShift, which is our leading platform for cloud computing, basically can enable you to spin up and take out all the different AI projects that you have, from pipeline all the way back to development and back again, to basically flexibly allow you to create an infrastructure platform that can get you into AI production that much faster. Because everybody knows about the timelines it takes to get an AI model into production, to wrap the application around it, to get it out there to test, and take a very, very good look at the behavioral characteristics. Well, what's interesting is this accelerates it rapidly. It really does. And I was fortunate enough to be on the sidelines watching Sherrod Griffin and Steve Hewells start that project. I think it was about 5 or 6 years ago, that then turned into this product that now Red Hat is very successful with. So we're really excited about that development. But what I think is even more interesting is what happens with AI workloads when you combine OpenShift AI with Kove, when you have that kind of a development and cloud platform that actually enables you to do hybrid cloud deployments in conjunction with a memory management technology like Kove's. The performance increases, the power savings, all these things have been very well documented by Red Hat in the lab. So I think what's really convincing to me, though, I think most of all, is to literally during a particularly demanding AI training run, or perhaps like AI anomaly detection, if you have a security system where you need to expand across all your memory instances for a particular workload or a traffic situation, et cetera, it becomes very, very powerful from that perspective. And you can use existing memory to enable those kinds of capabilities. So at Red Hat, being infrastructure folks, we really took a look at this. And at first, we're really scratching our heads. We couldn't believe it. But it really has happened. That last mile in cloud computing has been crossed. And Kove is the one to have done it. It's really, really exciting for us. So you're going to see a lot of work on the partnership side, a lot of work on the go-to-market side now. We're setting up labs at Red Hat right now, loaded with Kove and with Red Hat products, so customers can test this out. So please feel free to reach out to me on LinkedIn or any other aspect to talk more about this, because we're really excited to see this germinate and take place over the last 3 years. John?
Okay. All right, thanks. So what's involved in using Kove? Well, first of all, there are no code changes of any variety. You install the software, you hit a couple of buttons. I think it's 3. It installs, and it works on any piece of hardware that is supported by Red Hat in any way. So then you got to add some memory targets. So you hit another button. It installs on any hardware supported by Red Hat of any variety, and then you populate a memory pool. Memory over there, compute over there. And there is no limit. It scales linearly. So you can get any performance level that you want. It's your decision what you want, period. This has been used for over 10 years in a number of key places in the world. It's been used in supercomputing labs for a long time. We're in some of the biggest computers in the world. It is mature. It is not something that is a startup. This has been deployed for over a decade. We have customers who have memory targets that are 13 years old. Here's the way that people will use it. I'm going to install the software, and I just let it sit. I let the maintenance expire, because it doesn't matter. It doesn't matter that it's 5 generations older, because we hide the latency, right? Speed and performance and distance of cable are all latency. We hide latency. They just let it run. Okay, guess what? You let a machine run for 13 years, sometimes a machine will fail. Well, so what do you do on a server when it fails in your own data center? You turn it off, your support first person comes out, you take out some hardware, stick the hardware back in, you turn it back up, throw it back into the pool. What happens in our universe? You segfault, and in a blink of the eye, 200 milliseconds, you get a new memory allocation from a different set of servers. Let it hit you. Okay? We aren't storage, we're memory. So what's the state problem with a segfault and retry? We didn't lose data, we're managing the instruction set. We're thinking about the problem completely differently. So now I can have those servers over there, and this is what cloud vendors do, except on the compute side. I log into my cloud and I'm doing something. If it breaks, I request another time. That server behind the scenes is blacked out. You get a new server and no one could do it with memory because of the so-called latency. Well, now you can. Well, actually, you have been able to for about 14 years. It's just we didn't come out until recently on this in the public. Most of the people that we deal with don't permit us to ever discuss anything about what we're doing. We finally have a couple, but okay. Right now, you connect using InfiniBand. We will have Rocky support probably in Q4, definitely in Q1, G8. It's working right now. So you can go either direction that you want, if you want to do that. Okay, so now I've got all that done. I've got my memory pool, I've got my servers, I've got my edge circumstance, which is the same logic, where I've got some kind of a memory pool, maybe it's a server, maybe it's a couple, whatever I want to do. Same, it doesn't matter, we're hiding latency. We're not changing infrastructure, we're hiding latency. So I got to provision it. So all you do is you install whatever kind of virtual machine that you would like to install, Rev or VMware, and you hit another button. Now, this is the sophistication of using our software. You've now hit 3 buttons, okay? 3 buttons. And now you have the management console. And then you can type in about 5 minutes, provisioning rules. So you can say, well, I've got 100 terabytes over there of memory, and I got 200 servers. I'd like to give every server up to 5 gigabytes of memory whenever it needs it, between 2 o'clock in the afternoon and 6 p.m. Okay, type it in, you're done. But I'd like to have another where I can say that one of those servers needs to be 127 terabytes. How many people have bought a 127 terabyte server, right? Okay, this isn't the Superdome or 24 or 36 and pushing the limits of hardware. This is just, I made it, okay? Now, what about AI? We're all here for AI. So I've got a model running and I've got, let's say I've got 80,000 threads going. What is the probability that one of those threads out of those 80,000 is going to use more memory than is local, right? I don't know. Guess what? None of the programmers do either at that scale, okay? No one does. So what you do, because programmers aren't stupid, is you figure out, I'm going to back down my projected need for memory per node to, let's say, 25 or 30%, so that if any of those 8,000, 80,000, 8 million threads go too much, I've got enough memory that I don't lose my spot in queue. Think about it. This is what we do. What if you didn't do that? What if you just created a provisioning rule, because I got memory over that says, anybody that goes over memory, I'll give it to you for free. 200 milliseconds, shazam. I've solved the problem. That's how hard it is. And all you got to do is come over to our booth, and you can chat. We got a bunch of people there. We got a bunch of partners. We have a partner recently that's going to start building memory towers. You want a 100 terabyte, rack of DRAM? You can get it. This is about as easy as there is easy. Now, I want to give a little bit of perspective on this. One of our customers that we're allowed to talk about is Swift. Swift is the backbone of the international finance. Every 3 days, they process they transfer the global domestic product of the world, the whole world. This is trillions and trillions of dollars. They have to do fraud analysis. We're the backbone of this. So everybody here, you've already used our software, you just don't know it. This isn't like it doesn't exist. You actually use it. And here's what I can say. If we can work with them to solve that problem, there is no problem in this room that we can't work with you to solve. It is real. All you gotta do is try it. And with that, I think I can wrap this up and thank our folks here. So thank you. Thanks very much.
Thank you.